Okay, kids, we're back. Electric fields, section 7.3. We're going to figure out what this is. We've run into this word field before, but now we're talking about an electric field. We talked about gravitational fields in the past. You may remember that. And a field was a concept, a way of describing the influence of a particle, of an object, beyond its physical limits. So what we're saying here, or what we said in the past, was here's the Earth. It ends right there. That's how big the Earth is. This is where the physical matter ends. But away out here somewhere, there's a gravitational field. The influence of the Earth on other masses extends beyond its physical limit. Well, what we want to do now is here's a charged particle. The physical limit of the charged particles here. There's no more matter after this. That's where the particle is. But out here, all around it, it has an influence on other charges. How do we describe that influence beyond its physical limit? The electric field. So field, not a brand new concept, except we don't want to use field in the sense of gravitational fields, mass affecting mass, but electric fields, charge affecting charge. Once again, it's a vector field, little vector, wears a hat, okay? And once again, this is defined by the use of a positive test charge. Let me show you that in the picture here. So let's say you've got a charged particle and it's got a certain number of coulombs, positive Q coulombs, there's the particle. And in order to map out an electric field around a charged particle, what scientists have employed is a small positive test charge. That's what we use, a small positive test charge. So positive little q. And if that small positive test charge were right here, it would feel an electric force in this direction. And you could calculate how much that electric force is here. This is the equation we used in the last section. You've been doing some homework with it, all right? Well, how do we define the electric field, or at least the magnitude of it? Well, you take the magnitude of the electric force and you divide it by how much charge, how many coulombs are in the test charge. So we're going to plug in the equation for electric field. There it is. So I've plugged in the expression for it, and then I divide by Q, and I get an expression for the magnitude of the electric field is K, the electrostatic constant, Q, the charge at the middle that we're investigating, all over r squared. Well, what is r? R is a center to center distance. So if I wanted to know the electric field right here, I would have to know that distance r. If I want to know the charge right here, I'd have to know distance r. If I want to know the electric field here, I need to find out how far it is, this spot in space, from the center of what is causing the electric field. One thing I want to stress here, the electric field exists here and here and here and anywhere, regardless if there's a charge there or not. Just because there's no charge right here and I'm not physically testing it at this moment, we still understand that there is an electric field. It is still there. If you take a look at the equation, it's very similar to the equation for the gravitational field. Instead of the universal gravitational constant, we have the electrostatic constant. Instead of mass, we have charge, and we have r squared in the bottom. So very similar look there. Very similar indeed. So I've included some links to some simulations that show what the electric field would look like. They're trying to help us visualize this, okay? So let's not l- look into it too much. This is what the electric field looks like. It's an aid to help us visualize it. So charge 1 right now has no coulombs of charge. Then now it's got 1 coulomb of charge. See the air, it's positive. See how the arrows are pointing out? So we could picture the electric field like that. What about if it's 2? Oh, I get more field lines. meaning the field is stronger. It's trying to help us visualize it like that. 3, what's this go up to? 4, and 5. So the more charge here, the stronger the electric field around it. And that's for a positive charge. And we can also do it for a negative charge. But look at the field lines, they point in the opposite direction. Okay, and I put this link to this simulation onto the web today's announcement so you can see it. All right. Now, having only one charge at one time, that would be boring. All right. So we can have more than one charge. Watch. Let's say we have a positive charge. I don't know, let's make it 2 and another positive charge right there. So the field lines interact with each other right here. The field lines interact with each other and create this composite. If we bump it all the way to 5, that's what it looks like, helping us visualize what the field looks like. Now look right here, right in the middle. No field lines. So there would be no net or leftover or resultant electric field right there, to be none. I suggest you spend some time playing around with it, this will help get your mind wrapped up around it. So let's go to positive 5 now and negative 5. Very different arrangement as the electric fields uh, overlap with each other, add together to produce this resultant electric field. All right, so play around with that. It's kind of fun. Okay, kids, let's do an example. Here we go. Let's set up the situation here. You've got at this spot right here charge Q1 and it's negative 5.0 times 10 to the negative 5 coulombs right there. And then 0.52 meters away, you've got charge Q2 and it's positive 5.0 times 10 to the negative 5 coulombs. So the magnitude of the charges are the same, but this is negative, right? Negative right there, and this is positive. And what we want to calculate is there is this point here in space. There's no charge there. There's just a point in space there. And we want to find what the electric field is at that point A. So we want to calculate electric field at point A. That's what we want to do. Electric field at point A. Well, the electric field at point A is a result of the electric field at point A due to charge 2, which is in green right here. So if you think about it, this is a positively charged object. If I were to place a positive test charge there, it would feel a force straight upward, positive y hat. So that means that the electric field there, regardless if there's a test charge there or not, the electric field at point A due to charge 2 is all positive y. Now let's turn our attention to this charge here, Q1. How is Q1's electric field showing itself at this point A in space? Well, this is a negatively charged particle. So if I were to put a positive test charge there, if it's not there, I'm just using this idea to help me visualize. If I were to put a a positively charged small test charge right there, it would feel a force of electric attraction towards Q1. So that means that the electric field at point A, due to charge 1, is in the direction towards charge 1. So that's why I've written in the equation here that the electric field at this point in space, A, right here, is equal to the electric field at point A due to charge 1 plus the electric field at point A due to charge 2. So those fields added together. Well, let's try to visualize that. Here is my positive charge, here is my negative charge, and I want to find point A. Well, let's just for the sake of argument say that point A is right there. So the electric field at point A is pointing with a positive y hat component and some positive x hat component. That's what the electric field is right there. Here is another diagram to help us visualize that. So here's my positive charge. I go up a little bit, maybe to right there. Take a look at that field line, right? It's upward, the field line, and also some towards the positive. So we're finding the electric field right there that's being caused by these two charges. So you can see it's not straight up, right? It's a result of the charge here and the charge here, the sum of those electric fields at a spot somewhere around there. Here is another simulation, right? We want to find the electric field maybe right about there. If you look at the arrow, it's not straight up, it's kind of to the right. So here are three different simulations to help you visualize what the electric field would be like there. Now we have to do some calculations so we can actually come up with the quantitative vector with magnitude and direction to tell us just what the electric field would be there. And that's what we're going to do now. So here we are back at our note, and we have established the fact that the electric field at that point in space that we're calling A is a result of the electric fields of the two charges. Well, as always, components come to the rescue. So this here, electric field at point A due to charge 1, I'm going to break down into components. The x component of that, the y component of that. Also, the electric field at that point in space A due to the second charge, boom, breaking it down into components. There you go. All right. So let's do the electric field at point A due to charge 1 first. So what do we have to know? We have to know the magnitude of the charge, and we've got to know the distance. So that's 0.3 meters right there. So I've got that right here. Let me show you. I'll get my pen out. That is right there. I kind of mixed this up. Apologize. There it is. This term is right here. There's no x component, and the y component is positive. I get my direction from pretending, this is important, I pretend, oh, if I put a positive test charge there, what would be the direction of the force? Oh, it'd be straight y. All right? That's where I get the direction from, not from the calculation, but from the diagram. I can get the magnitude from the calculation. So K Q2 second charge all over 0.3 meters squared. So there is this term right here. Sorry for the little crisscross going on here. Now, this one right here, okay? This ordered pair I'm going to calculate from here. So, what do I need to know? Well, I need to know how much charge I have here for Q1. I'm giving it. But then I also need to know this distance right there, the distance from Q1 to that point in space A. Well, how am I going to calculate that? Well, it's pretty easy. It's a right angle triangle. Here's 0.52 meters along the bottom, 0.52 meters along the bottom, and zero point 0.3 meters going vertically. So 0.3 this way, 0.52 that way, and I get that the hypotenuse is 0.6 meters. So that's important because that's our R. The other thing that's really important to calculate, which you could calculate using trig, is what is this angle here? And you could easily calculate that to be 60 degrees. Why is that important? Well, it's important because the electric field at point A due to charge 1 is not all x, it's not all y, it has to be broken down into components as we were talking about a few moments ago. So I need to know that this is 60 degrees so that I can break it down into components where the x component would be opposite to the 60, so it would involve a sine. The y component is adjacent to the 60 degrees, so it would involve a cos. And look, the x component is positive, the y component is negative. I get that from the diagram. So that's what we do here. I now know it's K, Q1. What's the distance? 0.6 meters. Square it. And I've got to use the sine 60 to find the x component, and it'll be positive from the diagram. Over here, the y component. I know the y component is negative. Then k, q1 all over r squared, which we calculated r was 0.6 from Pythagoras, right? There's our r squared. And it's cos 60 degrees to get the component. So we have a positive component for x, a negative component for y. So now we just collect this x with this x, this y with this y. We collect it, and we do our calculations, and here's our answer right there. There is our answer right here. I did the calculation here. I did the calculation here. This was 0. I did the calculation here. And then I collected my x's together. I collected my y's together. And that literally, right there, kids, is the electric field at point A. And it is the result of these two separate electric fields that we've simply added together. Next, let's do another one. What would be the electric field? What would be the electric field right here at point B? All right, the electric field at point B. Well, I know that I need to find this distance, the distance from Q2 to this point in space called B, and the distance from charge Q1 to this point in space called B. Well, what do I know? I know the whole thing is 52 meters, 52 meters, or excuse me, 52 meters, 0.52 meters. I beg your pardon, 0.52 meters from Q1 to Q2. All right, and I've drawn B so it absolutely positively bisects this. All right, so each side would be 0.26 meters over here and 0.26 meters over here. So through Pythagoras, I can find out if I got 0.3 meters here, 0.26 meters there, I can find the hypotenuse. And the hypotenuse would be 0.4 meters on this side and 0.4 meters on that side. Now that I have these sides, I can also find the angle in here. The angle here is 40, and similarly, the angle there would be 40. So these are all important quantities that we're going to need as we try to find out what is the electric field right there. Well, let's try to use some of these simulations to help us figure this out. So we're saying basically find the electric field right there. Look at that arrow. Look at that. That's trying to tell you what the electric field is looking like at point B. Let's say point B is right there. Interesting. Make note of that. Here's another setup, kids, to help you visualize this. Let's say point B is maybe right there. Take a look at the direction of the electric field line. What is the electric field at point B right there? This will also help you visualize. Here's another one to help us visualize right here. What would be the electric field at this point B right there? Once again, the electric field being the sum of the electric field from the positive charge with the electric field from the negative charge. The two electric fields superimpose upon each other. So let's write out what we just saw on the simulation into an equation. The electric field at point B is equal to the electric field at point B caused by charge 2 plus the electric field at point B caused by charge 1 right there. Now, here is our point B right there. You have to keep in mind that the distance from point B to charge 2 and the distance from point B to charge 1 is the same. That distance is the same, kids. Look, right along there, 0.4 meters and 0.4 meters. The other thing you have to really keep in mind is the magnitude of these two charges is the same. The magnitude of the two charges is the same. So let's draw these electric fields right here. Here is the electric field at point B due to charge 2, and here is the electric field at point B due to charge 1. I've drawn them in black for you right there. Now, these two vectors have exactly the same magnitude, and because these two angles are the same, have exactly the same two orientations, the same two angles. So if this is theta, I'm calling this angle here phi. And right here, this is theta, and by opposite angle theorem, this angle is theta. And then also I have another phi here being the complementary angle. So not only are these two magnitudes the same, but their orientations are the same from x. One is up by phi degrees, the other one is down by phi degrees. That leads to something very beautiful, because if we break down electric field at point B due to charge 2, I break it down into an x component and into a y component, and then I do the same thing for electric field at point B due to charge 1. I break it down into an x component and a y component. Because these magnitudes are the same, and because we have an angle of phi here and also an angle of phi here, the y components cancel. They cancel by the fact that the magnitudes are the same and aided by the similar geometry. So that's what I've drawn right here. Electric field at point B is equal to the electric field at point B due to charge 2 plus the electric field at point B due to charge 1. I break them down into components as I've done here, the x component and the y component. I break it down into components here, x and y, all right? But the only thing that's left is the x component, and I've got two of them. And the x component is cosine to the phi angle. Here's phi, the x component is adjacent. Here's phi, the x component is adjacent. So what I need to do is find the magnitude of that electric field, K, Q. How far is it? 0.4 meters. Square it. Cosine the 50 degrees to get the component. And then, very importantly, I've got to multiply it by 2 because I've got two charges involved here. One is from charge 2, the other is from charge 1. It's just the geometry and the magnitude set up that the y's cancel, and I've got two identical x components. So since I've got those two identical x components, I've got a 2 right there. Plug in k, plug in the magnitude, which is the same for both of them, right? Look, I got magnitude signs here. So what if I plug in a positive or a negative? It doesn't matter. It's magnitude. The key thing about solving these questions is calculate the magnitude and get the direction from the diagram. Get the direction from the diagram. I cannot emphasize that as much as how important that is. So plug in the numbers and then you're done. And it's all x component. And okay. Okay, sorry about the little mix up there, kids. I didn't realize I was recording, but that's okay. The next thing I want to show you is how could we possibly create a constant electric field? Because we have run into constant gravitational fields, remember? Negative 9.8 newtons per kilogram. It's straight down. This is the gravitational field near the surface of the Earth, and it is most definitely a constant field. It doesn't vary. Well, how would I set that up for an electric field? Well, that is done by saying that a constant electric field is found between two oppositely charged plates. So if you can think of a playing card, and then just beneath the playing card, you have another playing card. So almost like in a sandwich situation, one piece of bread and another piece of bread, like in a sandwich. Between those two plates, you would have a constant electric field. So here's one playing card, here's another playing card. Between them, you would have a constant electric field there. And I think I have found, as I was toying around with that, yep, there it is. That's what it would look like. So right in here, we would have a constant electric field. One plate would be positively charged, the other plate would be negatively charged. So you can replicate a constant field, a constant electric field, to be like a constant gravitational field. It can be done. So going to give you some homework to do, some reading to do. Got this video made for you. Hope it helps out. You guys have a great day. Bye bye.